Hello and welcome to our lesson on functions. This is going to be from section 2.1 in our Precalculus text. We're going to start off with some terminology and definitions. The first thing we're going to cover in this lesson is a relation. You need to know what a relation is. It turns out that a relation is a correspondence, also known as a mapping or a set of ordered pairs, where each element of the domain, which are commonly the x's, corresponds to at least one element of the range, which are commonly the y's. Also, you need to know that for a relation, the domain is also considered the input, and the range is the output. Here we have three examples of relations. The first example here would represent a correspondence where we can see how x corresponds to y. The second example would represent a mapping showing each element of the domain and how it maps to each element of the range. And then last, we have a set of ordered pairs. So in this case, the braces, which are these funny looking parentheses on the ends, those are called braces. Mathematically, those are used to indicate a set. And here we have a set of three ordered pairs. So all three of these examples represent different ways that you can express a relation. Now that we have an idea what a relation is, and we've covered examples of a relation, now we need to talk about what is a function. Well, by definition, a function is a relation, therefore it has to be a set of ordered pairs or a correspondence or a mapping in which each element of the domain corresponds to only one element of the range. So here we have an example of a relation, and we want to determine if this relation is a function. So what we need to do is see if each element of the domain corresponds to only one element in the range. So here we have 1 mapping to 2. Notice that 1 does not appear in any other x-coordinate, so 1 only goes to 2. 3 also maps to 2, but since 3 does not appear as an x-coordinate anywhere else, that says 3 only maps to 2. 4 maps to negative 2. Again, 4 does not appear in any other x-coordinate, so 4 is only with negative 2. And 0 maps to itself. And again, since 0 does not appear in the x position anywhere else, 0 only maps to 0. So this would indeed be a function because each element of the domain maps to only one element in the range. So here we have another example of a relation. We have a set of ordered pairs, and we want to determine if this relation is a function. So checking the x's, here we have negative 1 that corresponds to positive 2. If you look back here at the back, we also have negative 1 corresponding to negative 2. So this would be a case of having the same x value that corresponds to different y values, which is a violation. This cannot be a function. And so again, this is not a function because you have negative 1, which is an element of the domain, corresponding to two different values in the range. And just so we have one more example, here we have another example of a relation. In this case, we have a mapping. We want to determine if this relation is a function. Again, the way we do that is we're going to check each element of the domain to see if it corresponds to only one element in the range. So we can see that 0 maps to A. Notice that 0 only maps to A. 1 only maps to U. 2 only maps to E, 3 only maps to O, and 4 only maps to I. So this would be an example of a function. Each element of the domain corresponds to only one element in the range. If you're wondering, well, what would this need to look like for it to not be a function? It's super easy. There you go. I'll just add that line. Now what you've got is you've got an element in the domain that corresponds to more than one element in the range, and now this relation would not be a function. All right, so now that we've talked about how to determine if a relation is a function, now let's talk about how to determine if an equation is a function. Well, the short answer is if y has an even exponent, the equation is not a function. Okay, so we're going to look at our first equation given here. Y equals 3x plus 1. Notice that that is also in y equals mx plus b form. We can see that y has a 1 for a power. 1 is an odd number, so this is definitely a function. The second example, again, y has a 1 for a power. I said if y has an even exponent, it's not a function, so this will be a function. And for the last example, notice that y here does have an even exponent, and so this would not be a function. So now that we've discussed the shortcut, the fact that y has to have an odd power in order for it to be a function, this is a great opportunity to introduce you to Desmos. Desmos is a free online graphing calculator where I've graphed our first equation, y equals 3x minus 1. You can see that we get this line over here, which is what we would expect for slope-intercept form. And we have a tool called the vertical line test to determine if a graph is the graph of a function. So what the vertical line test says, it says if I draw a vertical line and it intersects the graph more than one time, then the graph is not a function. So what I've had to do is be a little creative here. You can see that I've written an equation that's going to draw a vertical line, and I've also created what's called a slider so that we can move this vertical line back and forth. The reason is to illustrate that the vertical line, no matter where I put it, will intersect the graph only one time. So that demonstrates that this graph is the graph of a function, and therefore the equation would be a function. So to demonstrate the second equation is a function, here I've graphed it in Desmos. We can see that it is a parabola, which corresponds to the fact that it is quadratic. And again, if we move our vertical line back and forth, you're going to see that no matter where the vertical line is, it's going to intersect the graph only one time. And maybe you can see it better there with the dot showing. So again, this graph represents the graph of a function, because every vertical line that I could possibly draw will intersect the graph only one time. And for our last equation, again I've graphed that in Desmos. Here you can see that the red graph represents the graph of this equation. No matter where I move the line, we have a vertical line that touches the graph more than one time. And so again, this is not a function because it fails the vertical line test. All right, the next thing we need to discuss is function notation, and that is the f of x. You need to understand that f of x means y. So the reason that we have function notation is so that we can write things like this that tell us to do something. In this case, if I have f of 2, then that means to take the value of 2 and plug it in for x everywhere there's an x. We call this evaluating a function. So to find the value of f of 2, we're going to replace each x with 2, and then we need to work that out. So 2 squared is 4 times 2, that's going to be 8 minus 6, which is 2. And it's important to note what we have actually found here. Remember that this number is x, this number is f of x, which we said is y. And so what we really have found is an ordered pair. If x is 2, y is 2. And if we do this enough times and generate enough ordered pairs, we can plot the points and get an accurate graph of this function. All right, let's look at a few more cases of evaluating a function. Given this function f of x, we want to find f of a. So again, all you do is replace each x with whatever's in the parentheses. That'll give us 2a squared minus 3a, which cannot be simplified further, so that would be your answer. F of negative x, replacing every x with negative x. Here it's important to note that negative numbers or letters need to go in parentheses because a negative anything squared becomes positive. If you don't put the parentheses, you won't square the negative, you won't get a positive. So negative x times negative x is a positive x squared, leaving the 2x squared the way it was. But here, negative times a negative makes a plus 3x. Again, that cannot be simplified further. So that would be our result for f of negative x. F of 3x, replacing every x here with 3x. And then we're going to have to square 3x. So that would give us 2 times. 3x times 3x is 9x squared. Negative 3 times 3 is negative 9x. And then here, one more step of simplification. 2 times 9 is 18x squared minus 9x. That would be our final simplified result. And for the last piece of the puzzle, f of x plus h. This may be the most exciting piece we do here, where we're going to replace x with x plus h. Notice all of x plus h is squared, minus 3 times x plus h. And this is going to require several steps of simplification. So to do x plus h squared means we're going to multiply by itself, and that will indicate the FOIL method. The negative 3 can go ahead and distribute, giving us negative 3x minus 3h. Then the 2 needs to come down. You see the 2 is waiting his turn, and we need to FOIL. So first, x times x gives us x squared. On the outside, x times h, well, it's just xh. On the inside, h times x, I'm going to write that again as xh, and h times h is h squared. The minus 3x minus 3h come down, and here we've got one more step to go. We need to distribute the 2 and combine like terms. 2x squared. Notice I'm going to have a 2xh and another 2xh. Altogether will give me a 4xh, combining like terms as I go. And then 2h squared minus 3x minus 3h. There are no other like terms to combine, so this would be our final simplified result for f of x plus h. The next thing the text touches on is the difference between the implicit form of a function and the explicit form of a function. The easiest way I can describe this is the implicit form of a function does not have y by itself. The explicit form does have y by itself. So if we look at a couple of examples here, 3x plus y equals 7 would be an implicit form of a function where y is not by itself. If I move the 3x over, making it negative 3x plus 7, now it is explicit form. I guess another cool thing to notice is you definitely can tell if you have the explicit form if you can say f of x equals. And the only way you can say that is if y is isolated, if y is all by itself on one side. And then we can write this equation in function notation, f of x equals negative 3x plus 7. One more example, let's say x times y equals 1. Again, this would be an implicit form because y is not isolated, but if I divide both sides by x, giving me y equals 1 over x, now it's explicit. Now I can write it in function notation, and we're all good, and that's the difference between implicit and explicit form. The next thing covered in the text is the difference quotient. And here in the red box, I have provided the formula for the difference quotient. And I would like to look at least 3 examples of how this works so that you will know how to evaluate the difference quotient. So the first example I would like to look at is a quadratic function, f of x equals 2x squared minus 3x. In the difference quotient, the first piece of the puzzle that we need to calculate is f of x plus h. I'm going to do that in blue so we can try to color code this. To find f of x plus h, we're going to replace every x with x plus h. If you've been watching this video, you will know that we've already calculated this. So previously in the lesson, we looked at the function f of x equals 2x squared minus 3x. That's the same function we're dealing with. And we did calculate f of x plus h. Here's all the work for that. And this result is what we need. So again here what I did is I just simply copy and pasted the previous result. You can go back and review how we got this if you need to. The next piece of the puzzle is, well, we need the original function. F of x is 2x squared minus 3x. And now that we know f of x and f of x plus h, we can plug into the difference quotient. So that's going to give me 2x squared plus 4xh plus 2h squared minus 3x minus 3h. All of that is f of x plus h minus f of x, which is 2x squared minus 3x, all over h. And now we have evaluated the difference quotient, and now we need to simplify this fraction. We're going to distribute the negative. Notice that when I distribute the negative, that simply changes the signs, and then we can see the 2x squareds will cancel, and minus 3x plus 3x cancel. In the numerator, we have 3 terms remaining. Notice that all 3 of those terms do have an h, and so the next step would be to factor out the common factor of h. That will leave me 4x plus 2h minus 3. And now we can see that we have a common factor of h top and bottom that will reduce. My final answer for the difference quotient, 4x plus 2h minus 3, is the answer. For our next example of finding the difference quotient, we're going to look at a rational function. Here we have f of x equals 4 over x. So our first piece of the puzzle here is going to be to find f of x plus h. Replacing every x with x plus h gives us this function. The next piece, remember from the difference quotient, is simply f of x. Once you know f of x plus h and f of x, we can plug into the difference quotient. So that's going to be f of x plus h minus f of x all over h. And then we're going to need to simplify this. Here our ultimate goal is to get the h in the denominator to cancel. So as soon as you can eliminate the h in the denominator, you're done. In the numerator, I've got two fractions that I need to subtract. Remember, in order to subtract fractions, you need a common denominator. So the first denominator needs an x. If I give it to the bottom, I got to give it to the top. The second denominator needs the x plus h. Again, if I give it to the bottom, got to give it to the top. And now I've got identical denominators, so I can subtract the fractions. So we're going to have 4x minus, and this 4 is going to distribute. You do need to take this negative with it. So consider this as negative 4 times x makes a negative 4x, negative 4 times h, negative 4h, all over the common denominator. And then at this point is where I'm going to diverge from having the stacked fractions. Instead, I'm going to turn this into divided by h. That's so that it will help me remember to keep change flip. All right, next step, we need to simplify. 4x minus 4x, those are going to cancel, leaving negative 4h over x times x plus h. And then remember I said we're going to do the keep change flip, the KCF. Anytime you have division with fractions, you're going to keep the first fraction the way it is, change to multiplication, and the h, which is understood to be h over 1, we're going to flip it. And then we can reduce. We have a common factor of h top and bottom. And my final answer for the difference quotient is negative 4 over x times x plus h. And we're done. All right, for our last example of evaluating the difference quotient, here we're going to look at a radical function, specifically a square root function. F of x equals square root of x. Remember, to find the difference quotient, the first piece of the puzzle is to find f of x plus h. Replacing every x with x plus h gives me the square root of x plus h. The other piece of the puzzle I need, remember, is the original function, f of x, which I have, obviously. And then we can plug into the difference quotient, which is f of x plus h minus f of x all over h. Remember, I said that our ultimate goal is to eliminate the h in the denominator. So in this particular problem, I cannot get the radicals to subtract since their radicands are different. But what I can do is I can rationalize the numerator. Now, this is not something that's done very often, but it is going to be a necessary procedure here in order to get the h in the denominator to reduce. So, how does that work? How do I rationalize the numerator? Well, I'm going to multiply top and bottom by the conjugate, which is the same square root, let's call it stuff, same square root stuff with a different sign. And I'm going to multiply top and bottom to keep it legal. Remember, this is effectively 1 here. Multiplying a fraction by 1 does not change its value. And this is going to require the FOIL method. So we're going to go first, outside, inside, last, and we're going to execute the FOIL method with the radical expressions This should be fun. Square root of x plus h times itself would be the square root of x plus h squared, but we know a square and a square root cancel, so that's just going to leave me x plus h from the FOIL method. That's the first piece. And then on the outside, we're going to have square root of x times square root of x plus h. Let's leave those separate. We could multiply the square roots, but let's just leave it like that for now. Because on the inside, you're going to notice that we have a negative times a positive, which makes a negative square root of x times square root of x plus h. And now you can see the magic of using the conjugate, because what we have here are like terms with opposite signs. Notice that those are going to cancel. So this was the outside, this was the inside. Last but not least, we have negative square root of x times square root of x. Negative times a positive makes a negative. Square root of x times itself would be square root of x squared. Remember that a square and a square root cancel, so that would effectively just become x. And this is going to be all over the denominator, which is h times square root of x plus h plus square root of x. Now, let's see where we're at. We've got the outside and the inside. Those terms canceled each other out. So in the numerator, I simply have the x plus h minus x all over the denominator. And then if you notice in the numerator, we've got a plus x minus x that are going to cancel, which is going to leave me only an h. And now hopefully you can see that I'm going to have a factor of h top and bottom. So I'm going to write it like this. H only in the top is an understood 1h all over the denominator again. If I reduce the h's, notice that is going to leave me the coefficient of 1. And I'm to the end of the problem. Remember I said our ultimate goal is to get the h in the denominator to reduce, to cancel. And we have achieved that objective. So my final answer would be 1 over square root of x plus h plus square root of x. You may not like it, it may look nasty, but that's the answer. At this point in the lesson, the textbook wants us to focus on finding the domain of a function. And the domain are the values that x can be. Some functions are going to have restrictions on the independent variable. So we got 4 functions here we're going to look at to discuss what the restrictions may or may not be. The first function is a polynomial function, specifically a quadratic function. What you need to know is that the domain of every polynomial function is always all real numbers. In other words, there are no restrictions on the domain if your function is a polynomial. Now, there are 2 ways to write the domain. We can write the answer in interval notation or set notation. You probably should know both of these. So for the polynomial function, since there are no restrictions, x can be anything from minus infinity to infinity. That would be the domain in interval notation. The way you say that in set notation is you're going to use a brace. We're going to say the set of all x such that x is an element of the reals. This is the fancy math notation way to say x can be any real number. Next function, here we have a rational function. A rational function is a function with a fraction that has a variable in the denominator. and a rational function has the restriction that the denominator cannot be 0. That's your restriction for every rational function. And so to find the values that x cannot be, we're going to take the denominator, we're going to set it equal to 0 and solve. So moving the 4 over gives us x squared is 4. Taking the square root of both sides, that's going to give us x is plus or minus 2, and those are the values that x cannot be. So the easiest way to express the domain of g of x here is with set notation. We're going to say the domain is the set of all x such that, and then you simply write the restriction. X cannot be positive or negative 2. And that's the way the domain would look in set notation. Interval notation is going to be a little bit more complicated because x can be any real number, anything from minus infinity up to negative 2, but not including negative 2. So we're going to use a parenthesis and then a union symbol so that we can jump over to the other side of negative 2 and keep going up to 2, not including 2, skip over to the other side of 2 and keep going. So this would be your domain in interval notation, showing that x can be anything from negative infinity to infinity except negative 2 and 2. Next function, here we have a radical function, specifically a square root function. And a square root function has the restriction that the radicand, which is the stuff under the radical, must be greater than or equal to 0. Do you understand? That is the restriction for every square root function. The radicand must be greater than or equal to 0. So we're going to solve this inequality for t, and that will give us the values that t must be. Let's move the minus 3t over, which is going to give us 4 greater than or equal to positive 3t. Then if I divide both sides by 3 and flip the inequality, do you see the arrow points to the t? If I flip it, the arrow, the inequality still needs to point to the t. T is less than or equal to 4/3. So this is our restriction. To write that as the domain, remember you must use either set notation or interval notation. Here the set notation would be the set of all t such that t must be less than or equal to 4/3. And so that would be your domain in set notation. If we want to express that in interval notation, since t must be less than or equal to 4/3, t can be anything from minus infinity, that is infinitely less than negative 4/3, up to 4/3. We're going to use a bracket this time because it says less than or equal to, meaning that the 4/3 can be included. So this is our domain for h of t in interval notation. And we've got one more function to look at, capital F of x. Here this is a rational function with a square root numerator. This is an example of a function that's going to have two restrictions. Remember that a square root has the restriction that the radicand must be greater than or equal to 0, but we also have the restriction that the denominator cannot be 0. So we're going to have to consider both of these restrictions and then combine them to get the domain. Solving the inequality, we're going to have 3x greater than or equal to negative 12. and divide both sides by 3. X must be greater than or equal to negative 4. But x can also not equal 5. So let's look at that on a number line real quick. Sometimes it's easier to look at a number line sketch shading what x can be in order to write the domain. Here we can see that x must be greater than or equal to negative 4. That would represent a solid dot, or you could say a bracket, greater than or equal to negative 4. But as soon as we get to 5, x cannot be 5. So we would have an open circle showing that 5 is not included. So with this shading, it should be fairly easy to at least write the interval notation. The interval notation here would be everything from negative 4 up to 5, not including the 5, but we're going to skip over to the other side of 5 and keep going. Notice how this interval notation represents what is shaded. The set notation for this particular domain would be the set of all x, x is the independent variable, such that x is greater than or equal to negative 4, and the textbook shows just using a comma, adding the other restriction. So the set of all x such that x must be greater than or equal to negative 4, but also x cannot be 5. And so that would be the set notation for the domain of this particular function. On a side note, it is important to mention that there may be some functions that have an inherent restriction based on what the function is dealing with. Here we have the area of a circle written in function notation, where the area is in terms of the radius. Even though this is a polynomial function that would not have a restriction, it does have an inherent restriction because the radius in real-world scenarios can't be 0 or negative. So to express the domain of this particular function, in interval notation, we would say that the radius can be anything from 0 to infinity, where 0 is not included, or you could say it's the set of all r, where r must be greater than 0. And the last concept that we need to cover in this section is function operations. That would be addition, subtraction, multiplication, and division of functions. So to illustrate the function operations listed, we're going to start with f of x equals 25x squared minus 4, and g of x is 5x plus 2. We've got a quadratic and a linear function, and we're first going to illustrate f plus g, which can also be written as f plus g of x, which means to take f of x and add it to g of x. So we're going to recopy f of x, 25x squared minus 4, and simply add it to g of x. And all you need to do to add functions is combine like terms in this case. So I've got a 25x squared, he's one of a kind. I've got a plus 5x, he doesn't have any like terms to go with. But I've got a minus 4 and a plus 2. If I combine those, negative 4 plus 2 gives me minus 2. And that is the answer for f plus g of x. Next, f minus g, which can also be expressed as f minus g of x, is f of x minus g of x. So again, I'm simply going to copy f of x first. That is 25x squared minus 4 minus, and since g of x is a binomial, I'm going to need to put it in parentheses so that I will remember to distribute the negative to all terms. Simplifying, we're going to have 25x squared minus 4 minus 5x minus 2, and then we need to combine like terms. I've got a 25x squared, I've got a minus 5x, and here I have negative 4 minus 2, which will combine to make negative 6, and I'm done. Next, f times g of x, which would indicate f of x times g of x. In this case, I'm going to replace f of x and g of x with what they're equal to. Notice that I do need to put f and g both in parentheses to indicate multiplication. And since these are both binomials, we're going to do the FOIL method. So first, 25 times 5 is 125. X squared times x gives me x to the third. Next, on the outside, 25 times 2, that's going to give me a positive 50x squared. On the inside, negative 4 times 5, negative 20x. Last but not least, negative 4 times 2 is negative 8. I have no like terms. That is also in descending order. And so that is my final answer, simplified completely and written with good math etiquette. And last but not least, we have f divided by g of x, which can be expressed as f of x over g of x. And then I'm going to replace f of x and g of x with what they're equal to. Like so. If the fraction cannot reduce, you're done. That would be the final answer. But if either the numerator or denominator can factor such that we can reduce a common factor, you need to do that. I happen to notice that the numerator is the difference of two squares, so we're going to need to factor that. The difference of squares always has different signs. The square root of 25 is 5, so that's going to give us 5x and 5x. The square root of 4 is 2. So now that that's factored correctly in the numerator, we can see that we do have a common factor that will reduce. And my final answer, simplified completely, is simply 5x minus 2. That is the answer for f divided by g of x. And that's going to do it for this particular lesson. If you have any questions or comments, please leave those in the comment section below, or you can text me. And thanks for watching.